Good afternoon, everyone. This is the Intro to Cloud Native Buildpacks talk. If that's not the talk you're trying to attend, then you're definitely in the wrong room. My name's Terence Lee. I go by Hone02 on Twitter. I work for a company called Heroku. And to kind of, before we start talking about Cloud Native Buildpacks, I kind of want to talk about kind of where Buildpacks came from and kind of go from there. And then we'll get into the Cloud Native Buildpacks. So Heroku has spent a lot of time focusing on developer experience, and I think for most people that have heard of Heroku, you've probably seen this command, git push Heroku master. And this was kind of the main command people used to deploy any application that they wanted to on Heroku. And we started off as a Ruby-specific platform, but then in 2011, we basically released a polyglot platform called Cedar, and at the heart of that, that let us kind of do that was this technology called Buildpacks. And so what we did was we took all the kind of language-specific build components from our Ruby part of the build pipeline and extracted it into a thing that we called Buildpacks, and so we could basically build like these language-specific components that were all Buildpacks that all kind of slotted into our build pipeline. So if you're not familiar with Buildpacks at all, they are this source-centric way that are highly opinionated of how you construct a runnable, basically, application artifact from your source code. And the Buildpacks on the Heroku side, when they first came out, were made up of kind of these three executables, bin detect, bin compile, and bin release. Cloud Foundry has forked kind of the Buildpack. Since then, they've kind of split this compile into two executables, supply and finalize, which Stephen will talk about later on in the presentation. So detect allowed us to basically decide if this Buildpack was applicable for this application and determine if we wanted to run it. Compile kind of did kind of the meat of the work of actually like installing any runtimes. If you're running a JVM app, it'll run Maven or whatever to install dependencies, kind of do all that work, and then basically make your file directory be ready to actually be run, and release kind of handled all the kind of metadata information like what the running process type, if we could detect what that is, kind of any other resources and things, environment variables that need to be set to actually get your application to run. And then at the end of the Buildpack, when it's run, you get this, what we call that Heroku a slug. On the CF side, they were called droplets, but essentially they're just this tarball that sat on top of a stack image that we maintain for our customers, or a base image, and that was something that we maintained. With that, we had kind of two separate components that let us run your application. And to kind of give you a sense of like what a Buildpack actually does, since we started off as a Ruby platform, the Ruby Buildpack has been with us the longest, and we have well over millions of Ruby apps running on it. And one of the things that's nice that I think is a little different from how things are handled with Dockerfiles is that there is one Ruby Buildpack. So pretty much almost all of our customers use the one official Heroku Ruby Buildpack, and installs every supported version of Ruby that is supported out there for us. Goes and uses the community-supported dependency management system, installs those dependencies, and then really, if like you're running Rails, which is kind of the major web framework in the Ruby land, it goes and actually sets up your application so you don't have to do extra work to make your Rails app run on our platform. So that gets all encapsulated, and so we've been running it for over 7 years in production, and you don't really have to go and install a separate version of the Buildpack. So it's like the same version of the Buildpack, and we actually install the latest version of kind of the Buildpack. It's run almost every time. So we're all about like minimizing the kind of pain as you kind of as we make changes to the Buildpack. In 2012, we open sourced our Buildpack technology, all of our official Buildpacks that we had, all that source, so you can actually go to on github.com/Heroku and find those Buildpacks and actually just go download them and do whatever you want with them. People fork them, but what's cool is that we actually got a whole new set of new Buildpacks in that ecosystem. So languages that we didn't actually support on the platform. People built Buildpacks for them so they could run them on Heroku. Different ways to kind of build applications, different build pipelines, as well as like off-the-shelf software. So companies and other kind of open source software that want to make it easy to integrate on a platform, they could write a build pack to kind of ease that transition. In addition to build packs, we also had other vendors and providers in this space who adopted build packs as a thing that they actually ran in-house that weren't on Heroku. So some of these companies and software providers just ran Heroku build packs as is, and kind of other third-party build packs, as well as built their own kind of build pack ecosystem around this whole thing. And so coming back to kind of containers, which is kind of why we're all here, Docker build packs were kind of created before Docker existed. Even though we ran them in LXC on Heroku's end, they weren't really designed with kind of these container initiatives that we kind of know and love today when they were created. And so when people talk about containerizing their applications, I think most people think of you write a Dockerfile and you probably run Docker build, or maybe running Conoco on Knative or something like that. But that's probably how most people are actually going ahead and actually building these container images. And so I think Dockerfile is very powerful and flexible, and for a lot of users is actually really good, but writing a quality production Docker image that you want to ship into your kind of cluster can be challenging, I think, for a lot of users, because you have to take a lot of things into account. So as an example, this was on Hacker News fairly recently, I think within the yesterday or last few days. But basically, the official Docker Hub OpenJDK images were running and I think this is still actually true, but running a development version of OpenJDK. So if you actually go and download it, it's missing some bug patches and CV patches like in the thing you're downloading. So you have to think about kind of the stuff that you're pulling in and using. SNCC released a blog post about how the top 10 most popular Docker images contain all these vulnerabilities of just like dependencies that haven't been patched in the software that's being run. This is from the official Python image from Docker Hub, and so basically, like, I think this is a common thing that most people do when they first start using Dockerfile, but you have to know to kind of just like hoist out, because the way the interface for how you do Docker image building, how it's tied to the instructions that you write, that you need to hoist out the dependency management stuff from copying the rest of your source code in, so you don't have to kind of pay that file system cache cost every time you run Docker build for changing things that don't actually affect your dependency management system. Just general security best practices, you kind of want to not be running things in production with root basically that has access to everything. So just basing off the previous example slide, you probably want to add an actual user and then actually set that user before running the command. The kind of implication of this is probably dependent on your application, whether root is acceptable or not to be running in production inside the container. Continuing still with the Python example, so this is a super tiny screenshot, and it's not really important that you can read the lines, but this highlighted yellow thing from GitHub is from the Debian templates of the Python thing, and this is about 50-ish lines, and I think the Alpine one takes up more than one screen page worth of just one run instruction command to install Python. And again, this is about the interface of how this stuff works. In best practices, you kind of want to minimize the number of layers you're generating because it increases the size of your Docker image. And so kind of the best accepted standard to that is to actually run that as one single run command, so it only produces one layer. So you need to, as you're generating stuff, also clean up after yourselves. And so I think a common use case when you're kind of building these things out in production is that you have two images and you want to combine them together. For instance, say I have a Ruby application, but I need to interface with some SOAP or whatever interface, so I wanted to pull in like a Java library to kind of interact with that. So I think the answer most people will tell you in this space is just use multi-build. Multi-stage builds with Dockerfile, right? So I have this Ruby image, so I have this guest kind of JDK image. I'm going to pull this in as a multi-stage build and then copy basically the stuff from that image into my existing image that I'm already building. But unfortunately, If you know anything about this JDK image as you're building it, you know that this Docker Java home is actually a symlink. So I can't actually just copy this in because it doesn't actually, it's not a deep copy that will copy the stuff from the symlink. So I actually have to go through and inspect the image of what is actually in that folder and actually copy every single thing from that folder into my base image. It also doesn't copy environment variables, so I need to actually go and read that Docker file and how it's built and copy the environment variables that are needed to actually run with that Docker image. And of course, I actually want to copy the thing that's built from the JDK. But if we're running this in production, I also know that I don't want to be running JDK probably in production. So I also need a third image, which is the JRE image. And so once I'm done doing the build, I want to then copy the JRE image into my final image. So this is the final Docker image that I've had to generate, which I've had to basically dissect that JDK image pretty deeply to basically get a working Docker image. So they aren't really these kind of composable units that are these black boxes that we can just consume and use. We have to have pretty deep knowledge of how these images actually work. So short summary, you don't get environment variables, symlinks don't work. You have to actually understand where those things point to. There's a pretty limited amount of stuff you can do. It's really just file system stuff. So you can't do like glob stuff. So you end up with a ton of copy statements that we saw before just to get a working image. And as kind of further best practices to ensure that maybe you need a secret that you're using to actually go ahead and copy things into your Docker image, or maybe do like a private dependency install from your Maven repository. I think multi-stage builds are a great use case for doing that, but you kind of have to do this thing where you do it and then you want to ensure, it's a way to ensure that basically you will not leak those credentials into your final Docker image because they'll be part of a layer that gets kind of tossed away before it gets into production. And so all these things aren't necessarily super hard, but these are things that you have to take into account when you're just trying to do best practices around building quality production Docker images. And so with the customers that we interact with at Heroku, one of the things that is nice is that they want to come join and play and do all this stuff with containers, but they don't necessarily want to have to know how to do all these things. So I'm going to let Steven kind of take on the rest to talk about day 2 operations.
Thanks. Everybody hear me? Yeah, OK, awesome. So I'm Steven. I work at Pivotal on things related to Cloud Foundry and Kubernetes. Can I have the, thanks. And so we kind of took the build pack model that Heroku put together, kind of after Heroku open sourced build packs and their build packs and that model, but before Dockerfiles and Docker were a thing, and integrated that into Cloud Foundry as sort of the primary way that people build applications on Cloud Foundry. And today I'm going to talk about sort of day 2, which is like everything after your application kind of makes it to production, and what are the concerns, kind of looking at the Dockerfile model, looking at the current build pack model on Cloud Foundry and Heroku, kind of focusing on Cloud Foundry in my examples, and what it looks like to build an app and then keep it maintained in those models, and also in the Cloud Native Buildpacks model that this project is about, which I promise we'll get to at the end. So I'm going to kind of run through a case study of what it looks like to patch a high CVE in OpenSSL. And the CVE was, I think it was like a malicious ciphertext could cause a DOS. It was about 3 years ago. It was like a sort of high severity CVE. I'm going to run through Dockerfile again, CF model, and then Cloud Native Buildpacks model. So if you look at what like a Node.js app built using Docker images, you might start with operating system packages from Canonical that include OpenSSL, and then you might use the official Node.js image built on top of Trusty or Bionic or whatever, and then you might pull your application source code into it and build your sort of final image with layers from all of those things. And the model is that they're sort of linked together, like a linked list. Or that's how the Dockerfile model wants you to look at it. And so when there's a vulnerability in OpenSSL, that's kind of in the bottommost layer. And if you're a really large enterprise and you have 500 Node.js apps, then when the CVE hits on April 26th, you have a lot of imagery building to do. And this is kind of a problem. So if you're a big enterprise and you kind of tell all your developers, you have the power, go build your own images, do whatever you want, then you don't really have a great way of saying, hey, here's a secure, patched version of OpenSSL that you can go run. You have to tell them, go find wherever your base images came from and try to keep everything patched, and it will probably never happen for everything. But maybe you're a really good big enterprise and you do your Dockerfiles well, and you provide a corporate version of Node.js built on top of a trusted base image. I should probably say Bionic. I know Trusty is EOL now, but anyways, even if you do this though, the OpenSSL patch that Canonical is going to provide is ABI compatible. You should be able to swap it out from under all your other layers in a second without rebuilding anything. But in the Dockerfile model, you kind of have to rebuild all of these apps, and so that takes a long time. And so in Cloud Foundry, and also in Heroku, the model is very similar. I'm just using Cloud Foundry as an example here. We've always had a different model of kind of dealing with this. And this is one reason why we've stuck with Buildpacks for so long as opposed to moving over to Dockerfiles, is our users really care about these kind of operational concerns for patching things at scale. So we keep the application bits kind of separate from the base image bits. We build a thing called a droplet, or in Heroku it's a slug. That's kind of like, the buildpack is kind of like a function, and your application source code is transformed into this droplet object, and it kind of adds language runtimes and configures the application to work. And again, this is the current Cloud Foundry model, not the Cloud Native Buildpacks model. And so this droplet kind of runs on top of this base image we call it rootfs, but it's not linked to a particular version of it. The base image packages just get ABI compatible security updates, and if you're curious what that means, ABI compatibility is like a strong guarantee at the binary level that when Canonical or Red Hat or your operating system vendor, whoever they are, patch operating system packages, that they really try not to break compatibility so that you have a relatively strong guarantee that things don't break. And so when you have a vulnerability at that bottom layer in Cloud Foundry, we have a kind of interesting model for updating all of your apps in production. And it's kind of tied into the infrastructure too. So we spin up, and you'll see here we have two kind of, you could think of these like edge node VMs that are running applications. In this case, there are 2 VMs running 2, but in a big enterprise, this would be 100 VMs running 100 applications each, right? And so in this model, we spin up new VMs that have a new copy of the rootfs, and also a new copy of the VM base image to try to patch as much as possible, because often the same vulnerabilities apply to both when critical CVEs hit. And when all the apps start successfully in the new VM, we take down the old one and flip the routes to the new one. And we do this one VM at a time until all of your infrastructure is patched. And this lets you mitigate a critical CVE for every app on your whole foundation in a couple of hours for a very large foundation, less than that for a small foundation. And so now I'm going to talk about the Cloud Native Buildpacks model. And this is kind of the project that we're kind of here to talk about. It's a t-shirt. And this is kind of, we wanted to take the best aspects of the Buildpack model that we kind of developed out for 6 or 7 years, probably longer than that at this point. Take the best aspects from that, the kind of operational benefits from that, but also move to container standards like the OCI image format, like Docker registries. Build something that's not Dockerfiles, that's an abstraction that's useful for a little more useful for developers, where they don't have to think about the operational concerns, but always builds a secure image, and it lets us patch lots of applications at the same time. And so to do this, we kind of took that original model where you have this droplet or slug and the base image, and we play it out on top of a Docker registry. So where you have an image manifest for your individual application pointing at your app-specific layers in its own repository, but then also pointing across repository boundaries at dependencies that live in other repositories. And when there's this critical CVE hits, we just update. We upload a single copy of the new operating system packages to the whole registry once for maybe 500 apps, and then we make a small metadata change of that manifest for all of these, all your 500 images, right, to point to that new layer. And we can do this for 500 images in a few minutes or even less if you do it in parallel. It doesn't require any containers. It doesn't require any builds. It's just rewriting some metadata for each image directly on the registry, right? There's no downloading. There's no Docker daemon involved, nothing like that. And we can patch 500 apps really quickly. It's just a bunch of network requests after the single copy of the OS packages are uploaded. And to do this, I think a question we get sometimes is, why didn't you move to this model sooner? Why? What's the significance of doing this now? And the answer is, a lot of this, there are kind of two key features one in the OCI image format and one in Docker registries that are relatively new that we really couldn't use before. We couldn't move to the model because of. So the OCI image format or also the Docker v2 image format kind of moves to content addressable layers. So if your view of Docker images is that they're like a linked list, that's not really true anymore. Docker images are kind of a Merkle tree of image layer SHAs, and you can kind of manipulate them kind of at will directly on the registry if you want to. It's not that linked list that people have in their head. The model isn't really like Git anymore, and I think that's a common comparison people have. And the other feature is there's a thing called cross-repo blob mounting in the new Docker registry spec that lets you kind of point at layers that live in other repositories. And with those two things together, we can do this sort of really fast rebasing. And when I kind of walk through the model in a second, you can kind of see how other ways we take advantage of those capabilities. So to kind of walk you through what the new interface looks like, we had this detect and either supply and finalize on the Cloud Foundry side or compile on the Heroku side and release script or executables in the old buildpack interface, from however long ago. In the new interface, we still use executables in a bin directory, but it's just detect and build, and there's sort of metadata passed between them to kind of make multi-buildpack support work well with detection. So you can detect a series of build packs that all apply to the app and apply them, and I'll kind of go over what that looks like. And in addition to these two steps, there are two sort of infrastructure steps that are handled by the platform. And so in the detect, so I'll kind of run through everything. In the detect phase, an optimal selection of different build packs is chosen that apply to your app, and some metadata is generated about what those build packs are going to do during the build phase. During the analysis phase, we pull metadata about, if there's a previous image from a previous build, we pull metadata about that image and about the layers in that image so that during the build phase, the build packs can decide just to rebuild layers that actually need to change and leave the layers that don't need to change on the registry. They don't even have to, those layers don't even have to get downloaded. It just builds the individual new layers that need to change, and then during the export phase, uploads those to replace the outdated layers in the repository. And so I'm going to run through an example kind of what that build process looks like using Ruby buildpack and a Node buildpack. But I'll point out that like in Cloud Foundry, the Node buildpack now and the new API is actually 3 buildpacks. It's like a Node buildpack, an NPM buildpack, and a Yarn buildpack. So you can really go very modular with this if you want to. But just sort of pedagogical example here of what it would look like with a Ruby buildpack and a Node buildpack. So if your application had, say, a gem file and a package JSON and some app source code, and you're going to run it with a Ruby buildpack and the Node buildpack, first the Ruby buildpack would run, and if it passes detection, it would contribute something to the build plan that says, hey, I looked in your gem file or your gem file lock, and I found that this is the Ruby version that your app needs, and it writes this to the sort of metadata build plan. And the Node buildpack runs detection and says, yep, I'm a good candidate. That means the whole group passed, and so we can use this configuration for the build. And then it's going to contribute some metadata that says, hey, Node version 8.12 is what we're going to run with here. And then the build plan is fed into the build phase, which generates a Ruby layer and a gems layer of the particular versions. And then the build plan is fed into, build plan is fed into the Node build pack, and it runs its build phase, generating the Node.js layer and the Node modules layer. And so to kind of do this build by build, so you kind of get a sense of why the model is efficient, starting with that app, the first build, analysis happens and nothing happens because there's no previous image. Installs everything, installs Ruby, gems, Node modules, exports those layers out to create the image. And then on the next build, those layers are still there in the registry. They're not going to be downloaded locally. But let's say you upload an app with a different package JSON and a different gem file. During the analysis phase, we read information about all the layers. The build pack knows, oh, I don't need to rebuild a layer for Node.js or for Ruby. I just need to run bundle install and npm install to regenerate the things locally. And I even have the npm cache available. There's an interbuild cache that's separate from the layer cache. And then just the new layers that changed are exported out to the registry. And the whole thing is kind of stitched together back in the registry really quickly. And so if relatively little changes, then there's little rebuilding and little data transfer. And this means that some application builds on the old model that took 30 seconds go down to like milliseconds in some cases. It's pretty impressive. And then only that little bit of extra data is transferred all the way to the edge node because the layers stay on each node. And that's sort of my talk. That's sort of our talk, sorry. So if you want to check out Cloud Native Buildpacks, we have a kind of second public beta available. You can go to buildpacks.io for more information. It's also on GitHub. We have real Cloud Foundry and Heroku Buildpacks available now. They're all kind of Ubuntu-based, or those are the base images we have available. Join us on Slack also, and or a mailing list, and we have a deep dive tomorrow at 15:55. So please come to that too. We're going to dive into the sort of V3 Cloud Native, Cloud Foundry, and Heroku Buildpacks that we've been working on, and how those work, and kind of what the future looks like for the project and stuff. So please show up if you're interested.
Yeah, if you want to see the decomposition that Stephen talked about, we'll be going into that as well. So
yeah, definitely. Any questions? In the back?
How do you decide what kind of build pack you make? So with the example you gave of Node and Ruby, how does the build process decide which process is actually going to be run when actually it's
I think the question is, how does the build process decide which, do you mean like runtime is going to be chosen like between Ruby and Node, or do you mean like version of the runtime, like Ruby version?
actually be executed? Once that image is built, where's the metadata to start
Oh,
release script?
I see.
Define the entry points. Where's that defined in the model?
Got it. So at runtime, when the image starts, what sets the start command, right? So all the build packs, this is like after detection during the build phase, all the build packs can contribute process types. The process types are like individual start commands that you can choose between when you start the image. We actually hook the launch process. There's a thing called the launcher. It's like a Go binary that lives in the container, and that's set to the entry point. And then you can override the command to set a custom start command, or the launcher knows where to find the metadata that the build packs wrote out that have the different process type lists in them. And so you can set your command to something like web, and it knows, oh, run the default web process, and that gets executed. And so generally, the last build pack kind of wins for, currently that's the, currently that's the process where if you put like node at the end if you want to start your node process as the primary process that runs. But you could also run multiple process types at the same time if they contribute different ones too. If you're running on K8s and you want to do something with sidecars.
yeah, it's the last build pack in the build plan, I guess, as a
In the build order, but yeah totally. Cool. There.
So if I wanted to create a new build pack for a custom language or framework, how do I go about doing that? And what's the level of integration that's typically GitOps tools like, say, OpenShift builds and the other tools that you have that people are using to yield containers in production right now? How would I make it to work together that would be perfect? How do I go about doing that?
Yeah, so the question is, if you have a few different technologies on a platform, like how would you write build packs for those to work on a particular platform?
So you have a bunch of existing GitOps options that basically allow you to git push and build image that you can use in your deployment environment. The integration level with buildpacks would be one. And the second question would be Ruby and Node.js are great, but if I have a particular framework that I want to run, how do I go about describing a new buildpack structure?
Got it. So it's two questions. First question is like, how would you plug build packs into a GitOps workflow where you do a git push and you get an image out from the other end, right? And your next question is, if you have a custom framework or something you want to write, how easy is it to write a build pack that supports that and hook it in with other build packs in a build process, right? Cool, okay. So Your first question, so the tools we're providing as part of the project are a CLI that's kind of for local builds called Pack, that because sort of the core part of the project is called the lifecycle, and it's a set of binaries that run unprivileged reproducible builds in any containers. But if you're on a local machine, you need some kind of containers. And so it uses the Docker daemon to run containers in a row that build the image, not using Docker build, and those get exported. But then there are also these lifecycle binaries for when you're running in a cloud platform that can do the unprivileged reproducible builds in the cloud platform. So if you wanted to do a GitOps workflow, I think the most common thing people do right now is they use Knative build, and there's a template with that can pull from a Git repo and use a select, run the lifecycle binaries to select the right build packs and do a build with them and all of that. I think that's the thing I've seen most people do. There's a concourse resource also if you like concourse. I think we're working on some things too to kind of improve the infrastructure side and what that build looks like.
Yeah, and then Jason Hall ported it to Tecton too.
Yeah,
as well. So
right. Knative build is now Tecton too. Yeah. And so your next question was, how easy is it to write a build pack that kind of plugs in? So a lot of what we've done in the new build pack API is because it's like a break from the existing build pack API. None of the old build packs work without a shim on top of them, right? Part of that breaking change was to make it really easy to write new build packs. So if you've ever tried to write a Cloud Foundry or Heroku build pack right now, there are definitely some gotchas in that process because that was made a long time ago and it's been kind of ported across through containers. We've tried to make it as easy as possible to write a new build pack and to make it communicate to other build packs over a really clear contractual thing. So like in the Cloud Foundry side, our node build pack is a node engine build pack, an npm build pack, and a yarn build pack. And if you want to shim in an APM build pack before that, or your own custom thing to make some changes to the apps, you can just drop that build pack before the group identifier for the rest of it, and it usually just works. We've really tried hard to make that workable because both of us really care about strategies with partners and things like that, making sure that it's really easy to integrate into the ecosystem, ideally easier than it is to integrate into the Dockerfile ecosystem. Right? Does that answer your question?
Yeah, I mean, on the if you go to github.com/buildpack, that's where you can find pack and lifecycle and all the stuff Stephen talked about. There's also a spec repo in there that has basically the specification. It's not quite like here's a tutorial how to do it because it is the spec, so it's a lot more formal and has kind of a lot of nitty-gritty details that you can do, but I think for most build pack authors, they don't actually need to understand a lot of the spec to actually write one. There's a lot of power and flexibility added to the spec for kind of more advanced use cases as you need to kind of do things. So like even all the caching layer stuff we talked about here, you can actually just write to this app layer, which is the third one from the bottom, and not deep. Like basically, it will be like kind of the old build pack model where it was not built in the Docker image context, and so you can have really simple build packs that don't take advantage of kind of these other primitives if you want to do that. So
it's like like a progressive complexity model. It's really easy to write a simple one, but then you can really take advantage of a lot of the fancy features if you want to. There's also we also have docs that kind of walk you through writing a simple Ruby build pack, just if you want to kind of understand what the experience is like too. Cool.
Cloud Native Buildpacks, is the intention ever to produce Dockerfiles as the result of the Cloud Native Buildpacks, or this is an alternative to
Yeah, we don't use Dockerfiles
Can
anywhere.
Repeat the question.
Oh yeah, sorry, good point. The question is, do we generate Dockerfiles? Do we plan to generate Dockerfiles as part of the project? And the answer is nope, we don't use Dockerfiles anywhere. We manually build OCI images straight from unprivileged, capability-free containers, and we do so in a reproducible way, which is difficult with a Docker daemon. So you don't need something like Conoco or Builda or whatever. We use Go libraries, a Go library Google wrote called Go Container Registry to just write directly to the registry to kind of construct these things kind of as efficiently as possible. So we can't really generate Dockerfiles because we do that. But if you do want to use a Dockerfile to extend your app afterwards, you can say you can start a Dockerfile, say from the app you had, and do whatever you want to afterwards. It's not because it's using the OCI image format, which is the Docker image format. It's just as compatible as anything else, right? Cool. Say it again. I'm having a little trouble hearing you. So your question is,
If you're not using Docker, like how do you do the equivalent of a run in a Dockerfile? So like you need to do a VM install.
got it. So the question is like, if we're not using a Docker daemon to do a Docker build, how do we manage creating containers and running things inside of them? Time's up?
Yeah,
Okay.
I think that's our last question, basically.
Cool. Yeah. How do we manage, running the containers in the platform to build the images? And the answer is the image where the build happens on has the same or a compatible base image as the image that the layers get exported to, and so it all kind of just works together. But let's chat afterwards. We gotta wrap it up.
Yeah.
Thanks.
Yeah, thanks everyone.